Now, this presentation is an opportunity for me to show you what I've done in my research and my views on this field of energy geotechnology. But equally important, or perhaps more importantly, is an opportunity to imagine our future. And with that in mind, I have two goals for today. One is to show you how civil engineers are at the heart of the energy transition and energy challenges that we will face in the next decades. But two is to show you how, by understanding geomaterial behavior, we can address some of those energy challenges. And let me start with the following statement. Civil engineering is all about quality of life. And you may argue otherwise, but if you start to track the major developments of civil engineering throughout history, you will realize that that indeed is the case. Earlier in the 1900s, the emphasis was on infrastructure, to build the roads that we sit upon, to build channels that allow trade, and a clear example of that is the Panama Canal. In the 40s, population was growing, demands for energy, demands for water increased, so we started to build dams. In the 60s, we realized our infrastructure is very sensitive to earthquakes, and with the field of earthquake engineering and things like liquefaction started to emerge. And in the 80s, it was about the environment, right? The major environmental disaster led to the field, or led to the creation of this field called geoenvironmental engineering. And I hope I'm able to convince you that the next challenge that we're going to face, or one of the big challenges that we're going to face in the next decades, is energy. And folks, energy is so ingrained in our societies that we sometimes give it for granted. But clearly, without energy, we don't exist. That's basic thermodynamics. And the picture you're seeing here is called Earth at night. And it gives you a sense of how sparse energy is, or it gives you also a sense how certain countries tend to consume more energy. And in fact, those countries are the ones that tend to be more developed, the US, Europe, so forth. Well, let's try to convince ourselves that that is the case with some data. And here what I'm plotting is energy consumption per capita for different qualifiers that quantify quality of life. And remember, this is ties to the concept of quality of life. Civil engineering is all about quality of life. And clearly you see, as energy consumption increases, you have more access to water, your life expectancy increases, you are more educated, and the overall health of the society increases. And by the way, each of these data points is a different country. And folks, I have lived in 3 different countries in my life: Colombia, Saudi Arabia, and the United States. And I can testify that these relationships hold true. Now, where does this energy come from? Traditionally, it has been a fossil fuel dominated energy mix, right? Petroleum, gas, and up to 20 or 15 years ago was coal. But perhaps a more important question is, how does the energy of the future will look like? And to answer that question, we don't know, right? But we can make projections, right? And this is only one of those projections, but I think all of them agree that the renewables will see the fastest growth among all energy resources. We are talking that we're going from a 9% as of today to a 25% by mid-century, and that's a huge growth. So the challenge is as follows. We know population growth is happening, right? Population will increase. We know that quality of life demands energy. So we know those two things combine and lead to an increase in energy consumption, right? We know that is going to happen. But then we need to supply that energy in a way that mitigates the impact on the environment, right? So when we talk about energy challenge, we talk about a dual challenge: an energy supply, but doing it in a way that mitigates the impact on the environment. Now, how does this relate to the geo fields, particularly the geotechnical engineering field? And I think we can look at this in different ways. We can look at the resource itself, right? Clearly fossil fuels, we have extracted those. But on the renewable side, we have geothermal energy as a renewable energy resource, right? And the idea here is to extract that heat from the subsurface. And to support other renewable systems, such as solar and wind, we need minerals. And those minerals come from the mining operation. So clearly, the geofields and the geotechnical field addresses each of these problems from the resource perspective. Now, there is another component to this, and it's the implications of those resources in the form of geological storage. For these fossil fuels resources, we have waste, we have byproducts, CO2, produced water, and soil. And the idea here is that we need to permanently store those in the subsurface. And then we need to be able to inject those byproducts deep underground. And for resources such as solar and wind, we know the question that always is brought up is what happens when the sun doesn't shine or the wind doesn't blow. And to address that question, what we can do is to store excess energy and when the sun doesn't shine and the wind doesn't blow, we remove that energy from the ground. And we can do it mechanically in the form, let's say, of compressed air or compressed gas, or we can also store the thermal energy. And in that case, we need to be aware that this is a cyclic injection and withdrawing cycles of energy. And of course, for the mining operation, we have all the tailings and all the disposal of waste. But folks, in all of this analysis, the characterization is critical, the infrastructure to build this system is critical, the monitoring with time of these structures is critical. And these three things are at the heart of what geotechnical engineers do. So the message here is that the geofields, particularly the geotechnical engineering field, touch every single aspect of the energy challenge. Now, this field doesn't end with the application of energy itself. This field is wonderful because it allows us to expand what we know by going into new dimensions. And what do I mean by that? For example, in classical geotechnical engineering, you build a foundation and you think that that foundation is going to last 100 years, let's say. So your designs are expected to last 100 years. Within this energy geotechnology field, let's say you're, in the example shown here in this image, is a nuclear waste repository. Now you need to design those to last for 100,000 years. So we are stretching the scales at which we think and which we make our designs, not only in time, but also in length. Another example of that is fluids, right? We have in geotechnical engineering, we have thought about water and air, and these desiccation cracks are a clear example of that. But in this field, we need to we widen our spectrum of fluids that we work with, right? And a clear example of is methane hydrate, which is something that I will address later in the presentation. And another example of that is that, for example, here in the case of liquefaction, we have thought about mechanical stresses and hydraulic processes and dissipation and things like that. But in this field of energy geotechnology, we need to evoke new physics. We need to evoke thermal processes, chemical processes, and how those interact with each other. So clearly, the energy geotechnology field doesn't end with the application, but expands the processes and things we can explore. Now, how do I fit in all this? I am a person that explored the multi-physics of geomaterials, and I've done that by addressing three types of geomaterials: hydrates, fracture rocks, and carbonates. There is a different aspect of each of them for applications for energy, for storage, and a little bit about infrastructure. And the approach that I have adopted tries to combine the experiments with a little bit of modeling and field data and take advantage of the synergism between them. Now, let me give you a few of the examples of things that I have explored, and let's start with hydrate-bearing sediments, particularly the things that I've done to understand the viscoplastic behavior of these systems. But first, what are hydrates? Hydrates are these molecules that are composed by a water cage, shown here in red and white, and inside that cage you have a guest molecule. Typically, or in natural system, that is typically methane, but it can also be CO2, it can be other things. And at the micro scale, they look like this, they look like ice, right? And with any phase transition problem, these molecules like to live in a certain pressure and temperature space. And for hydrates, that's high pressure and low temperature, right? This is where hydrates live. And it turns out that hydrates are quite important. They can host up to 20% of the organic carbon in the world. And the map that you are seeing here is where hydrate has been identified. Each of these triangles is a location where hydrate has been identified. And you can see clearly they are in all continents, right? They are along continental margins or in permafrost region. And the reason for that is that those areas have high pressure, low temperature, and availability of methane for the hydrates to form. And the application of this not only relates to energy, right, but it also relates to climate change and global warming. Imagine all this methane is being dissociated, being released to the atmosphere, what is going to happen with the climate, but also with the landslides. Imagine this hydrate melts and what is going to happen with the stability of the seafloor in those cases. Now, what is special about hydrate? Why should we care about them? What is, why they are interesting from the scientific point of view? And I think they belong to this category of composites. They are granular materials that have three phases in the pore space: water, here shown in green, gas shown in black, and hydrate shown here in blue. And by the way, this is from an X-ray image, so this is how they look in reality, right? And the other aspect of hydrates is that imagine you have a sample from the bottom of the seafloor, you take it all the way to the surface. By the time that that sample reaches you, all that hydrate is gone, right? The temperature has increased, the pressure has decreased. So when you end up is having like a mousse, right? Which is far from being representative of what is happening in the subsurface. So in order to properly characterize these systems, what we need to use is a technology called pressure core technology that allows you to maintain that hydrate stable the entire time. So what is special? Well, the measurements are extremely complex because you need high pressure and low temperature to maintain the hydrate stable. Your typical soil models are probably not too realistic because you have this composite nature of different phases inside the porous space. And something that I really didn't talk about, but the gas production of hydrates is an extremely complex process. Once hydrate dissociates, your temperature decreases, your pore water becomes less saturated, it refreshes the pore water, right? So the salinity decreases. And then you have also the mechanical processes and the changes in effective stress and things like that. So it's an extremely complex process to understand. And to study these systems, I was part of an expedition in the Gulf of Mexico, and I thought I would give you a sense of what a hydrate expedition entails. You go to offshore, you go in one of these drilling vessels, right? Then you take away a drill string through a 2-kilometer water depth. And this is the image shown here on the left. Then this is the seafloor, the bottom of the seafloor. And then you need to drill a well. Let's say it's a 1-kilometer well, right? To reach the hydrate layer shown here in green. For those of you who are not familiar with drilling and drilling offshore, this is quite an impressive accomplishment because you're trying to take out 8.5-inch pipe diameter through 2 kilometers water column to drill 1-kilometer well. So if you think about the aspect ratio of that well, if you divide the diameter versus the length, that is equivalent to have a hair from your head that is 1 meter long. That is quite impressive. And imagine that you're trying to steer that in the water where the currents are pushing your pipes and all that. So that's quite an impressive accomplishment. But then let's say you drill your well, you get to the bottom of your well where the hydrates are. What do you do next? You need to sample. Well, then you need to sample them at pressure with the technology that I was describing earlier. So how does it work? You have a drill string shown here in light gray, and at the bottom of that drill string, you have a drill bit. And then that is shown here in this image on the left. And then that sits at the bottom of your well. Then with a wireline, you deploy this tool. This is the pressure coring tool. And that with the wireline, the tool goes inside the pipe and it latches at the bottom. And at that point, you start coring. You start rotating this drill bit, and then you get your sample. But then you need to seal that system to maintain the pressure at in situ conditions, right? And there are different sealing mechanisms, right? But one of them, one of the critical ones is here at the bottom through the action of this valve. And let me show you a video of how that actually looks. This is, by the way, high speed, this is 8 times lower than it actually looks in reality. And let me play it again. So the sample goes originally through this orifice And then once you seal it, that this ball valve rotates and seals the system. But then imagine that you're trying to do this, that looks trivial, but you're trying to do it for something that is 3 kilometers beneath you, right? And for those of you who are familiar with hydraulic seals, every time that you try to seal, you try to clean your surfaces to make it as clean as possible, right? But here you're 3 kilometers, this is 3 kilometers beneath you, so this is quite complicated process to try to do this. But then, okay, let's say you get your sample, then you take it to the lab. Now you need to cut your sample, right, to do some testing. And once again, this needs to be done at high pressure and low temperature. So what we do is we take the sample, which is stored in one of these vessels or chambers. We connect that chamber to an equipment such as the one shown here on the left. We pressurize that equipment, right, to the pressure needed. And then at that point, we open this valve. We grab the core with this manipulator. We scan it for X-ray, and we measure P-wave velocities to try to identify where the good quality samples are. And at that point, we start cutting, right? Once again, under pressure, we start cutting internally of this chamber. And once the sample is cut, we push it into a testing chamber. And for those in the geotechnical field, the testing chamber, it looks like a typical triaxial device. Your specimen sits here, and you can independently control the confining pressure of the radial pressure or stress, and you can also independently control the axial stress that you are imposing in your sample. You have control of the bottom and top sample pressure, so you can run hydraulic conductivity measurements, for example. And let me show you an example of tests that we've done with this device. The tests we have emphasized are uniaxial strain compression tests, meaning that we don't allow the sample to deform sideways. So once again, for those familiar that are in the geotechnical field, this is similar to an odometer test, right? But again, we're doing it in a triaxial device. Now, what I'm plotting here is axial strain versus effective stress. And let's focus on the blue line. The test starts here. We start loading. And at these discrete intervals, we hold the axial stress. We hold this value and we keep it constant. And what you're seeing is that the sample is deforming every time you hold the stress. And what that means is that the sample is deforming under constant load, something that we call creep. These samples are creeping. And just to convince ourselves that this is a consequence of that, we have hydrate in the pore space. We run the same test, but without hydrate-free, with material that is made of the same grains that the pressure core. And this is shown here in this black curve. And when we do this axial stress hold, we see the sample deforms very little in comparison with the pressure core. Now we run a test where we didn't have any stress hold for a hydrate-free specimen, and that's this gray line. And you see that hydrate-free specimen deforms more at a given stress level than the pressure core. So the interpretation of this experimental result is that the hydrate is increasing the stiffness of your material, but at the same time is promoting the creep. Now we're looking this in effective stress space, but we can look this on time for a particular stress hold. Here I'm showing void ratio, but this is the same data set, and clearly the sample is deforming with time, right? Following this an S-shaped curve. But now we have, again, this was a triaxial device, so we can measure what is the stress needed to maintain this uniaxial strain condition. So what is the radial strain needed to maintain this condition, right? And we can plot that using this concept of the stress ratio, which is basically the ratio between the radial stress over the axial stress. And that's shown here in this red curve. And what you're seeing that with time, the stress ratio goes up and it starts to plateau around 1. And what that means is that the radial stress is increasing and is approaching the axial stress. These systems are becoming isotropic, or the stress states in the system is becoming isotropic. So what do we think is happening? We think that the hydrate shown here in green is bearing some of that load, but the hydrate acts as a viscous fluid that with time starts to flow, and deform. The grains rearrange themselves, and we have compression. But at the same time, the hydrate is pushing the lateral boundaries and the stress ratio increases. Now, this is our intuition, this is what we think, but we need to put these experimental observations into a mathematical framework. So the model that we have for compression in hydrate-bearing sediments is that any stress that is applied to a hydrate-bearing sediment can be decomposed to the stress borne by the soil skeleton, or also, and also in addition to that, the stress borne by the hydrate skeleton, right? And with this concept in mind, we can do many things, but one of them is to try to explore this in the spring and dashboard concepts. And with this simple model, we can replicate the decrease in or the compression with time, and at the same time, we are replicating the increase in the stress ratio with time. Now, what are the implications of this viscoplastic behavior? What should we care, right? And earlier I said hydrate can be important for landslides, right? That's an observation that we have seen from data. But the thought there has been that the hydrate dissociates, the material loses its strength, right? This hydrate melts, and then you have the landslide. But with this experimental observation, what we can actually think about is that these hydrates behave like a glacier, that there is actually a slow creeping movement, and this hydrate is deforming very, very slowly. Now, another important implication of this is that imagine you have stress versus depth here, and you have a hydrate layer. Your horizontal stress will be very close to your vertical stress in these hydrate layers, right? And that has huge implications of how we drill wells, how we complete these wells, and so forth. All right, let me switch gears here a little bit. And this was hydrate, going from pressure cores, experimental observations, to a little bit of modeling. But now let's explore fractures, right? And here the question is, well, first of all, what is a fracture? A fracture is a discontinuity in a rock mass, right? And the question here is, for fractures that have experienced shear, such as the one shown here on the left, what are the implications of that shear for flow behavior? And one way to think about that is by analyzing a single fracture at a single scale, right? What happens if you shear this fracture? What happens with the flow through that fracture, right? Now, why fractures are important in the context of energy transition, and it turns out they are critical for these systems called enhanced geothermal systems. And the way this works is that you have a very hot rock, and you need to extract that heat from the subsurface. One way to do that is you inject a cold fluid, let's say water, cold water. That water gets heated up, and then you recover a hot fluid, right? But there is a caveat. Most of these hot geothermal systems are hosted in rocks with extremely low permeability. So what you need to do is to artificially create flow pathways that allows this water to flow, this closed loop to occur. And we do that by creating fractures. And the energy stored in these geothermal systems can be quite large. We're talking that it can in fact exceed the amount of energy stored in fossil fuels. Now, there is a problem when we try to study fractures, and they vary in a wide range of spatial scales. If we think about fractures as a subset of mechanical discontinuities, let's say they vary from 100 microns to, let's say, 10 meters, right? There is 5 orders of magnitude. So the question is, how do you study something that varies so much in length scale? Or in fact, perhaps a better question is, what is the common parameter in fractures that are big and in fractures that are small? And that parameter is roughness. And the way we have characterized roughness is by using this concept of power spectral density, which is a concept used in the signal processing community very often. But what this concept is all about is that if you have a surface, that surface you can decompose it as an arrangement of asperities, each one with its own amplitude and its own wavelength, right? And what this plot tells you is that the bigger the wavelength, the bigger the amplitude, right? And that makes sense. In nature, you don't have a stack of needles, right? But perhaps something more important about this plot is that, or what this plot is telling you is that the relationship between amplitude and wavelength is the same for large-scale fractures than for small-scale fractures. And that's a very powerful concept, because imagine that you go to the lab and you measure a surface, right? You measure the topography of a surface. With this concept, what you can do is that you can numerically generate a surface that looks like the one that you have just measured. And because this relationship holds for small scale fractures and large scale fractures, you can extrapolate that to much larger systems. But roughness is only one part of the spectrum, right? You need to realize that fractures are composed of two surfaces, one on top of each other. And then you need to wonder how those two surfaces talk to each other. And they talk through this concept of matedness. Matedness describes how well two surfaces are correlated. And to think about this, let's think about extremes. Imagine a perfectly mated fracture, right? One on top of each other. The two are identical. Or an unmated fracture, a perfectly unmated fracture. There is no correlation between the two surfaces. And let's start to shear those. And let's go to a perfectly mated case first. As you shear it, your fracture will dilate. You will create void space between your surfaces. You will create aperture. And we can think about these on histograms as zero shear. There is no aperture, right? Zero, everything is zero. But as you keep shearing it, as you keep shearing the fracture, you start dilating more and more and more. But then the interesting case happens when there is an unmated fracture, because as you shear it more and more, nothing is happening. And why is that, right? And by the way, these are the result of multiple numerical realizations. So these are statistical relevant values. And so why these things doesn't change, why the aperture doesn't change with shearing unmated fractures? Because you are shearing something random on top of something random. So the net result is something random, right? Shearing makes sense when there is some degree of correlation between the two surfaces. Now we can explore further this concept of digital analogs, working with fractures numerically. We can start to study different processes, for example, flow processes, right? And here we have studied the effects of normal stress, right? Imagine you have a fracture and you load it normally from 0 MPa to 15 MPa. And then you flow through that fracture, right? And the contour maps that you see here are flow rate magnitude. And what we're seeing is that as you increase the flow rate, the normal stress, your flow starts to get channelized. Certain areas of the fracture start to carry most of the flow, right? So what we say here is that normal stress promotes flow channeling. And for shear displacement, what we did was we have a fracture that we start to shear it, right? And then you start to see that these topographic ridges start to emerge transverse to the shear direction. And why is the case? Why is that the case? Because as you shear it, the contact points transverse to the shear direction starts to get detached, right? And then you create these topographic ridges. And the consequence of that is that you will induce anisotropy in your flow field. Now, I'm an experimentalist and I like to do experiments. You saw it in the hydrates part. And I like to develop my own tool. So this is a tool that I developed. It's a pre-fracture specimen where you can independently apply normal load, torsional shear, and you can independently control your flow, right? You can inject any type of fluid that you want. And some of the examples of the data that I have acquired with this device, here is transmissivity, which is the analogous of permeability in fractures, versus shear displacement. And as you see, as shear progresses, the transmissivity increases, right? Both for, let's say, for 1 megapascal or 2 megapascal, right? What we're seeing here is that dilation that I showed earlier, right? But we went beyond the measurements and we started to develop models that can anticipate this behavior, right? And those are those solid lines. One aspect of these models is that they must satisfy asymptotic behavior. What happens if shear goes to 0? What happens if shear goes to infinite, right? And that's important because in a numerical simulator, if something goes to infinite and then your transmissivity go to infinite, let's say, that will generate an instability, right? So we did this with that in mind. And the models are working great, are anticipating the behavior we're seeing in the lab. But then we thought, well, what about data that others have acquired, right? And that's what we did here on this right-hand side plot, right? We compiled data from multiple labs of transmissivity versus shear displacement, and we superimpose our models, right? And then we see our model predictions capture well the data, not only ours, but the ones that others have measured. Now, so far, what I have talked is about fractures in single phase, right? Let's say only water flowing through the systems. But energy systems have multiple phases, right? And I showed that earlier in the hydraulics example. And then you need to wonder what happens if you have multiple phases in a fracture media, right? And in the way we have typically studied flow processes in, let's say, in homogeneous porous media, is by using these dimensionless plots, right? And these dimensionless plots tell you what are the relevant forces that you are interested in. In this case, viscous forces and capillary forces, right? And if you inject a fluid with certain conditions of viscosity and things like that, you may form a stable displacement or you can form some type of fingering, right? But then, once again, the question here is, what is going to happen in a fracture media in these cases? And to study that, we use a technique called microfluidics. It's a technique that allows you to manufacture pores with the size and shape that you want, and then observe the flow behavior through a microscope. So the way we represent fractures are these thick lines that you see here. And within those thick lines, there are small, tiny lines, and those represent a matrix, right? One critical aspect of this design is that we make sure that these are thick micromodels. Why? Because if you go back and you look at the capillary pressure equation, you will realize that there are two dimensions to this problem, right? The depth, but also the dimension you are seeing through the microscope. And then we want to make sure that the one we are seeing through the microscope is the one that controls capillarity. So we make sure that these micromodels were thick enough. And let me show you an example of a test that we've done. We have injected water and it's displacing air, right? And we injected very low, very slow, right? Very low flow rate. And we inject, and then we start, the water is yellow. We start to see how water preferentially invades the matrix, the small channel, the small pores. Why is that? And we think that that's because in this case, what is controlling the invasion is the matrix capillarity. The matrix is sucking those fluids in, right? And that's why the water goes preferentially through the matrix. But if we inject very high flow rate, what is going to happen? Let's say we increase the flow rate 1,000 times. And now what is going to happen is that the flow will go preferentially through the fractures, right? It goes preferentially through the fractures first. And why is that the case? Because when you are at these flow rates, what is controlling the invasion are the viscous forces. And in those cases, the fracture have a prevalence to flow through. And because we have this transverse fraction, we may have these pockets of air trapped. But these are experimental observations, right? Once again, we need to put them into a mathematical framework. So our analysis was relatively simple. We're going to assume that the matrix channel can be represented by a cylindrical pore, and our fractures can be represented as two parallel plates. And we do this because with these simple approximations, we can come out with analytical expressions that tell you how fast fluids flow through these systems, right? And if we take the ratio of those times, right, we can come up with a dimensionless ratio that will tell you if your flow is going to be controlled by capillarity, by the capillarity of the matrix, or by the advection through the fractures. Now, let me close the presentation with some closing thoughts. And I think this energy geotechnology field is critical to quality of life, which is at the heart of civil engineering, right? There is a dual challenge here, right? Population growth, increasing quality of life, drive the increase in energy demand, right? But we need to do that in a way that minimizes the impact in the environment. This field is critical for the energy transition, but it doesn't end there, right? It's also allow us to extend what we know of geomaterials, right? Thinking of long time scales, thinking of coupled processors, and things saturated or sediments and rocks saturated with complex fluids. For the civil engineering field, I think there are wonderful opportunities for research. for the teaching perspective, it made us renew our emphasis on the basics, on the fundamental understanding of fluids and forces, but also it opens the spectrum of engineering application that we can work with. And for the practicing engineers, I think we are well positioned to address those energy challenges in a field that is filled with resources. I've shown this slide. I have shown this slide earlier, but I think I want to reiterate that the emphasis of the Energy Geotechnology Lab will be problems that address or that are addressed using a multi-physics framework, a multi-scale, and they're interdisciplinary. Thank you so much. I'm happy to answer any question.
Does anyone in here or online have any questions?
Yeah, go ahead.
Yeah, so based on your experiments and modeling of the fluid flow and fractures, which do you think is best applicable to geothermal energy capture?
Yeah, so I think with geothermal, they're all relevant. The processes that I described are relevant for geothermal. In geothermal, you will have changes in effective stresses, you will have changes in flow rates and these things, right? And in fact, it can even extend to multi-phase flow because geothermal system can have vapor present together with water, liquid water, right? One aspect that I didn't address, but which is critical for geothermal, is the effect of temperature, right? What is going to happen with your fracture when you change the temperature field, right? What is going to happen with the permeability? What is going to happen with your stresses and things like that? So I think there are opportunities there to explore this further.
Hi, Carlos. This is Andre Buckling here at the Bureau. So I have a question which may be indirect, but can you comment, do you think this lab studies can shed some light into the, what's the exact mechanism of the microseismicity happening with the fluid injection and how can we deal with them?
Well, that's clearly something that I have not addressed yet, right? But with microseismicity, what you have, there are changes in your stresses and how your pore pressure dissipates, right? And I think some of those things we can explore with these concepts that I have presented, right? But it's something that I haven't really thought too much about it, so I cannot really elucidate a lot on this. But clearly, I think the fundamental physics of microseismicity are there. It's just that we need to explore them further. Yeah. Sorry, I wasn't very eloquent with my answer, but yeah.
Thank you. No, I know it's a difficult subject, but I feel that there are a lot of speculations in this area, which predict what kind of happens at the scale you're talking about without ever visualizing those mechanisms in reality. So I think I understand that it's a challenging phenomena, but if any light could be shed, I think that would be very, very valuable.
All right. Thank you for your suggestion. Yeah, absolutely.
So you mentioned in your sort of introduction about when the sun doesn't shine and
Right.
doesn't glow, and then you talk about storage. And I would have immediately thought just batteries.
Right. Yeah.
But you seem to suggest something else.
Yeah.
Can you explain a bit more?
Yeah. No. Thanks for bringing that up. Yeah. So batteries. The problem here is about sizes, right? You need to store a lot of energy. Batteries have a limited capacity in the amount of energy they can store. If you want to store a lot of energy, you need a battery that is huge, right? And I think that's the biggest problem with batteries, right? They have a limited capacity to store large amounts of energy. So I think that's why the subsurface works as big giant repository for energy. Now, batteries are critical for transportation, right? For electric vehicles, those sizes would work great. But I think when we talk about electricity generation, things like that, we need to look at different parts of, or complementary technologies to address this. Yeah. Absolutely. Thanks for bringing that up.